Hey everyone! In this video we are going to be looking at examples of how to assign oxidation numbers. If you haven't already, check out our previous video on the rules for assigning oxidation numbers. This video is just going to be a set of examples. So let's start off with example number 1. And example number 1 is going to be aluminum chloride. Now, aluminum chloride is just a binary ionic compound. In binary ionic compounds, each ion is simply assigned the oxidation number of its usual charge, which means our aluminum is +3 and our chloride is -1. Anytime you see binary ionics, easy peasy, just give them the numbers. And even if we get one that has a transition metal, so FeBr2, if I say the name out loud, you're going to know what it is immediately. The bromide, this is binary ionic, the bromide's -1. You can figure out, because there are 2 bromides and each one is -1, that this must be an iron 2 bromide, so the iron is +2. Again, all of the ions just get their charge as their oxidation numbers. We'll do some easy ones here. If you just have aluminum metal, just aluminum metal as a solid, pure elements have an oxidation number of 0. Now, those ones are easy to assign. Oxidation number 0. And same thing if you have a copper solution and it's copper 2+ and it's dissolved in water. This is just like a binary ionic compound. It's just an ion. It's monoatomic. It's not a polyatomic ion. It just gets assigned the oxidation number of its charge. Time to ramp this up a little bit. Let's go ahead here with number 5. In number 5, we are going to have CH4. Hopefully everyone remembers their oxidation rules, because the first question I always ask is, got hydrogen? If you've got hydrogen, and it's not one of the very rare examples where hydrogen is not +1, hydrogen's going to be +1. We know that the sum of all oxidation numbers in a neutral molecule has to add up to be 0. There's 4 hydrogens, so whatever carbon is, let's just say that's X, plus the 4 hydrogens, 4, has to equal 0. I believe that you clever little cupcakes can math this out. X has to be -4, which means in this case, the carbon has an oxidation number of -4. Let's do another one with carbon, CH3Cl. And we begin with, got hydrogen? Do we? We do. We have 3 of them. Hydrogen gets assigned +1. But we have a carbon and we have a chlorine that we need to deal with here. When given 2 elements that are not hydrogen or oxygen, we assign the preferred charge to the most electronegative atom. In this case, between carbon and chlorine, the most electronegative is the chlorine, and when chlorine forms an ion, it prefers to be -1. Now, same as in example number 5, we have to figure out what's left of carbon. So we have an X, there are 3 +1 hydrogens, +3, the chlorine is a -1, -1, this equals 0. The +3 and the -1 becomes X plus 2 equals 0, and that works out to be a -2 for our carbon. So our carbon can have an oxidation number not of 4 or -4, but it can even have ones in the middle, like -2. We'll scroll this up and we'll get another one going here. Number 7. NO3-. So we have a nitrate polyatomic ion here. First question I always ask, got hydrogen? No, we don't have hydrogen this time. The next question that we ask is, got oxygen? We do have oxygen. And unlike those few examples where oxygen is not -2, oxygen is almost always -2. Now we can solve our nitrogen. But in a polyatomic ion, instead of adding up to be neutral, it's going to have to add up to be the charge of the polyatomic ion. So we end up with X. There are 3 -2s So that's minus 6. It's going to equal a negative 1 instead of a 0 this time. We rearrange to get x by adding 6 to both sides, and it's going to leave us with an x value equal to 5. The oxidation number of our nitrogen in the nitrate polyatomic ion is going to be 5. Let's try another example that involves polyatomic ions. If we have magnesium hydroxide, in this case, the magnesium is still just a monoatomic ion, which means we can just go ahead and assign it +2. Magnesium is an ion that prefers to be +2. This is an ionic compound. It just gets the +2. The OH is a hydroxide, so we can actually treat it just like a hydroxide. We don't have to work it out like the whole molecule. Got H? We do. It's +1. Got oxygen? We do. It's -2, and this works out because the oxygen is -2, the hydrogen is +1, and their sum is the -1 for the hydroxide. So I'm just going to put the -2, and I'll put a little 1 + 1 underneath the hydrogen right there. And that's how we assign those oxidation numbers, even though this is a polyatomic ion. 2 more to go here. Number 9. We'll do something a little trickier, and we'll have C6H12O6. Glucose molecule, loving the bio, throwing that in here. Exact same set of questions we are going to ask. Got hydrogen? We do got hydrogen. Hydrogen's going to be +1. Got oxygen? We do got oxygen. Oxygen's going to be -2. Here's that moment where I ask, what do all the oxidation numbers of glucose have to add up to be? I really hope that you just shouted that out loud and made me like giggle in delight. If you didn't, you gotta step up your game. You gotta step up your game. We have 12 hydrogens that are +1. That's a 12. Our oxygens, we have 6 -2s, that's -12. This is going to equal 0, and we have 6 carbons. So we actually write this as 6x. Now, if we were working out this algebra, at the end we'd have to divide by 6, but here's the funny thing. Because it's 6x + 12 - 12 equals 0, we end up with 6x equals 0, and x equals 0. In the glucose molecule, carbon actually has an oxidation number of 0. One more to go. I'm going to do one last polyatomic example here. This time, sodium phosphate. Hopefully, all of the rules are starting to stick in now. You realize this is an ionic compound. In an ionic compound, if we have any monoatomic ions, start off just by giving them their charge. Sodium is monoatomic. It's a +1. We can look at the phosphate separately. Because phosphate's a polyatomic ion, we would ask, got hydrogen? We do not got hydrogen. Got oxygen? Oh, we got some oxygen. It's assigned -2. Because phosphate has a charge of -3, the sum of all of the oxidation numbers has to be -3. So our phosphorus, which is an X, we have 4 -2 oxygens, so that's -8. It's going to equal -3. We add 8 to both sides, and it leaves us with an X equal to 5, which is the oxidation number of our phosphorus. So we can go back and fill these in, +5, -2. And that, you clever little cupcakes, is 10 examples of how you can be assigning oxidation numbers in a mixture of ionic and molecular compounds. Thank you very much, and I'll look forward to seeing you next time.